Good afternoon, everyone, and welcome to the Composites One demonstration zone. My name is Neil Smith, and I'm one of the technical support managers for Composites One. So we strive to be a solutions provider for you just as much as an industry-leading warehouse and materials distribution provider. So let's dive into our demo here today, and let's have some fun. So the braided sleeve that we're working with today from A&P, really conformable. It is a braided commingled nylon carbon sleeve, kind of a mouthful. Again, the nylon is commingled and combined with the reinforcement, in this case, the carbon reinforcement. We're going to be using this sleeve to produce this part for our demo today. This was made obviously in a prior part cycle. And if we can zoom in briefly on our two-piece aluminum tool, we can see, again, the part that was made previously on our previous part cycle, right here. So the process that we're going to be using for our demonstration today, typically referred to as bladder molding. Basically, if you're not familiar with it, what that refers to as, we inflate the silicone bladder, fairly high temp capable silicone bladder with 120 psi of air pressure. And the end fittings, as you'll see when Nate loads the tool a little later, the end fittings lock within the two-piece aluminum tool, and of course seals the air pressure inside of our silicone bladder. Now essentially bladder molding utilizes the positive pressure inside of our bladder, silicone bladder, and forces the commingled carbon nylon sleeve to the inside surface of our aluminum tool once the tool is bolted together.
So today we're basically going to make the shape that Neil showed, going from a large diameter to a small diameter to a hexagon, all on a curve. So trying to lay this up with non-conforming materials would be pretty difficult. There would be a lot of cutting, or kind of just placing materials, and repeatability would be difficult. But with the sleeving here, we'll see just how easy it is. So there's a lot of ways to lay up sleeving, but what I did here is basically pre-cut my 6 layers to length. And what I'm doing now is just essentially stuffing all 6 layers inside of each other. And what we're going to end up with is our 6-layer preform, so to speak. And since this is a demo, we want the ends to look pretty net shape. I'm basically going to come and trim off the excess material so that everything's the same length in our part. And then what we're going to end up with is this sleeve of material that, again, I'm going to kind of expand and just slide right over top of our bladder so that we're ready to put this into the tool once that comes out. So again, in just a matter of about a minute there, we laid up our part.
And Nate's going to grab those, and he's going to load the bladder with the sleeves into our tool. If we could get a close-up over there of him laying it up, and now going to make sure the sleeve doesn't capture between the tool halves. And again, you get to see how the fittings lock in the end to hold our bladder in place. And so while Nate's tensioning up and basically just snugging up our half-inch bolts here to make sure that we resist against the pressure from our bladder, transfer our mold over. He's going to put that on what we call our transfer table. And he's going to hook up our air line. And he's going to slowly apply the air pressure. Now, like I said, we're applying 120 psi of pressure. Quite a lot of pressure. That's about 7 to 8 times atmospheric pressure, 7 to 8 times the exerted force from a vacuum bag. So now what he's doing is he's going through what we call a pressure cycle. What we found was that when the bladder slowly expanded into the braided sleeve, the sleeves decreased in length. And so when the sleeve decreased in length, it had a tendency to capture our bladder And so by pressure cycling, we're able to basically reseat our bladder, get a more even consolidation and better quality part. So now Nate is going to lower down our heating plates over on the right side, and we're going to slide our mold with our inflated bladder at 120 psi onto our heating plates. He's going to raise the heating plate back up, and he's going to hit our cycle time. Cycle time is really only there just as a point of reference for you and for us, and it should be about 6 minutes. So I'm going to keep an eye on our temperature here. We're about 315, 320 degrees. Our thermoplastics process is really driven by the application of heat. So our cycle times are really driven by how fast we can get the heat in the mold and how fast we can get the heat out of our molds. As a result, we can get very fast cycle times with reinforced thermoplastics.
As Neil said, heat management really is the most important thing. We have to get that heated up, we have to get it melted, we have to get it flowing. So as we heat up, we're going to pass two kind of critical numbers. The first one is the glass transition temperature of the material, commonly known as a TG. So as we hit that temperature, the material is actually going to begin to soften. It's not flowing yet, but it starts to get soften up, and you can kind of move it around and reform it that way. As we keep heating up, we're going to hit the melt temperature. At melt temperature, the resin actually begins to flow. So today we're using a commingled material. So we have polymeric fibers blended with dry carbon fibers. So we need those polymeric strands to melt and flow into the neighboring dry carbon. So we need to get above melt temperature for this material. Today we're processing nylon, and we're going to be shooting for, as Neil said, about 440 to 450 degrees Fahrenheit. A lot of different thermoplastics out there with different melt temperatures and TG temperatures. So it's really a matter of kind of working with our customers to dial in what they're looking for. So we timed it pretty well here. We just hit 440. Neil's going to lower this down, and we're just going to slide it on over and let those cold plates pull some of that heat out.
With a little bit of trial and error, we determined that our demold temperature, optimum demold temperature, was around 200 degrees Fahrenheit. That obviously has, is a pretty large contributing factor to overall cycle times with how fast you can release the thermoplastic. And it's loosely correlated with your glass transition temperature, right? So in our case, we're gonna wait here until we're at about 200 degrees Fahrenheit, and I'm going to cut off our air pressure. And I'm going to bleed the pressure out of our bladder. I'm going to disconnect our air here. And I'm going to bring over our finished part for Nate to be able to demold on our demold table. And it came out really, really easily as well with the CAMX release system. And it's come out really clean and really easy every cycle we've made so far.